How many people are needed such that the probability of at least 2 of them sharing birthdays is 50%? A few days ago, Flocky was celebrating his birthday when suddenly Rex and Leon surprised him with a self-baked birthday cake. Flocky, already suspecting to be bamboozled by his friends, has also prepared a surprise. A riddle of probability. Consider the following. Let A be the proposition that 2 people celebrate their birthdays on the same day of the year. If there are 2 people in a room, the chance of the 2 sharing birthday is 1 in 365. If there are 366 people, since there are only 365 days in a year, at least 2 of them must share birthdays, making the probability 1. Now the crucial question. How many people need to be inside the room such that the probability of 2 of them sharing birthday is at least 50%? Rex and Leon, being perplexed by the riddle, first guess 183, since this is 365 divided by 2. Intuitively, this argument seems believable, but does it hold? Let's do the math. To calculate the probability, we first investigate the probability of not A, meaning the probability that none of the involved people share birthdays. Since a single person cannot share birthdays, P of not A, given 1 person in the room, is 1. Now if a second person joins the party, P of not A given 2 people in the room is 1 times 364 by 365. Think of it this way. The first person in the room has a birthday. The second person has only 364 days left in order to not share birthdays. This equation can be rewritten as 1 by 365 squared times 365 times 364. Let's double once more. If there are now 4 people in a room, the equation reads P of not A given 4 people in a room is 1 divided by 365 to the 4th times 365 times 364 times 363 times 362. Here, the purple multiplication chain of decreasing numbers comes from the ever-decreasing number of days in the year where no one celebrates his birthday. If more people enter the room, this multiplication chain will increase in length with the same pattern already established. Let's investigate the purple term a little further. We can rewrite this as a fraction as such. Here the complete denominator cancels out, leaving only the chain 365 times 364 times 363 times 362 in the numerator. The trained eye recognizes now the beauty of this formulation. Rewriting this using factorials yields purple is 365 factorial divided by 365 minus 4 factorial. This leaves us now with the general formula for the probability of no one sharing birthdays within a group of n people. P of not A given n people in a room is 1 by 365 to the nth times 365 factorial divided by 365 minus n factorial. Kitty now recognizes that the formula we just derived is, in a sense, the opposite of what we were looking for. In probability, it is a common trick to calculate the probability of an event A by subtracting the probability of not A from 1. This leaves us with the formula for the probability of 2 people sharing birthdays as P of A given n is 1 minus P of not A given n. The probability of 2 people having the same birthday can now be plotted as a function of the number of people, looking like this. Here the x-axis corresponds to the number of people n, and the y-axis to the respective probability of at least 2 people sharing birthdays. Because of the clear convergence for bigger n, we only plotted the range of n from 1 to 80. The point where the graph crosses the probability of 0.5 corresponds to the 50% probability Flocky asked for in his riddle. Reading the value for this point on the x-axis yields the result n is 23. So it only needs 23 people in a group such that the probability of 2 of them sharing birthdays is at least 50%. Thanks Kitty for showing us the graph. Only 23? Rex and Leon cannot believe that their intuition was so far off. In fact, they share their misjudgment with our viewers. According to this poll, where many of you participated, not a single person arrived at the correct answer of 23. Flocky, having investigated this brain teaser closely, has 2 remarks in order to explain the seemingly paradoxical result. First, it seems as if many people misinterpret the question. The number of people needed in a group in order for oneself to share a birthday with one other person is indeed 183, but the number of people needed such that the probability of any 2 people sharing birthdays is 50% is much smaller. Second, although 23 seems like an impossibly small number at first, think back of when you were younger. Remember those 2 people in your class or in your sports team sharing birthdays? Almost all people we asked had at least one similar memory. If the number of people for such a shared birthday would be as high as people expect, almost none of us would have such a memory. Although seeming more convinced than before, Rex and Leon still have some doubts. Kitty enters the stage again and offers a hands-on experiment. Let's simulate the situation at hand in order to confirm or contradict our theoretical findings. By the way, hit like and subscribe so we can afford more food for the members of the science gang. For the simulation, we assume that each day of the year is equally likely to be the birthday of any random person. In other words, the distribution of birthdays is uniform. We start with an empty room where we assume n, in this example 4, random people inside this room. Each of these people has a randomly generated birthday. We can now compare the birthdays and check if at least 2 of the people celebrate on the same day. To increase the statistical accuracy, we can refill our room with new random people multiple times. Kitty simulated rooms containing n equals 1 to n equals 80 people, where she collected data from 100, 1000 and 10,000 individual rooms for every number n, resulting in, for our most extensive experiment, 800,000 individual rooms that we evaluated. Let's see the results. Equal to the last time, we plotted the theoretical function in orange. We overlaid the results of the simulation in green. This first plot shows the simulation where each room was filled with new random people 100 times. We see that the theoretical values are approximated, but the scattering remains quite significant. Let's ramp the simulation up and see if we get better results. The second graph shows the scattering for the simulation where each room was refilled 1000 times. The simulation now widely agrees with the theoretical prediction, implying that the calculations were most likely correct. Now let us increase the data density one more time and fill each room 10,000 times. This leaves us with this result. The theoretical prediction now almost perfectly agrees with the simulation, leaving no room for speculation. The theoretical prediction is correct and experimentally verified. Who would have thought that it only needs 23 people for the probability of 2 amongst them sharing birthdays is bigger than 50%? This is a very counterintuitive and fascinating result of probability. Although seeming wrong at first, there is no doubt that this result is correct. If you managed to stick by until now, thank you very much for watching, and maybe there are some other videos on our channel you might enjoy. Check it out and see you soon!